Hello, this is Professor Evans again, and this video is for EET 1214C, and we are going to discuss voltage, current, resistance, and Ohm's law as it is applied to a DC circuit in this video. So our only learning objective is to learn how to apply Ohm's law to a series or a parallel circuit with a DC source. So in a previous video, I discussed the ideas of electric charge, voltage, current, and resistance. I'm going to do a quick review here just to recap what we discussed previously. So we discussed that electric charge is a property of matter that exists because of an excess or deficiency of electrons, and that we have like charges that repel and unlike charges that attract. And this idea of charge is how we get the concepts of voltage and current. So voltage is defined as the amount of energy per charge available. And voltage is what moves electrons from one point to another in an electric circuit. It's an electromotive force that causes electrons to move. A voltage source provides that electrical energy or that force, and it is responsible for establishing current. Voltage can be supplied from batteries, fuel cells, solar cells, generators, or electronic power supplies like in our labs on campus. Current is the amount of charge that flows past a point in a unit of time. Remember, current is a flow rate represented by capital letter I. Resistance is the opposition to current. It is expressed in ohms, symbolized by the Greek letter omega. When drawing a schematic for a circuit, our symbol for resistance looks like this. Our symbol for a DC voltage source looks like this. And these wires represent connection points from one element of the circuit to the next, and the wires are where current will flow from one element to the next. So just to recap, we have voltage measured in volts, represented with a V. Current measured in amperes or amps, represented with a capital I. Resistance measured in ohms, using the Greek letter omega, represented with capital R. And then again, we have our water pipe analogy showing the ideas between current, voltage, and resistance as related to a water pipe. Voltage is the force that causes electrons to flow. The flow of electrons is current, and resistance is the opposition to that flow. So in this class, there are two kinds of circuits we're going to discuss: DC or direct current circuits. Those circuits have a constant voltage or current supplied from a power source. So we're going to set up our electronic power supply, we're going to set the voltage to a certain level, and it's not going to change. Later in the semester, we'll talk about AC or alternating current circuits where the voltage supply does change in the form of a sinusoidal waveform. So we'll talk more about AC circuits in another video. Today we're going to focus on DC circuits. Our unit on DC circuits will introduce you to EET 1015C, which is our Fundamentals of DC Circuits course. Our unit on AC circuits will introduce you to EET 1025C, which is our Fundamentals of AC Circuits course. So as you think about the courses you're going to take next, most of you will end up taking DC circuits and then AC circuits, and this unit is a preview of what you're going to be learning in DC circuits. When analyzing DC circuits, a simple and helpful tool is Ohm's law, which describes the relationship between voltage, current, and resistance. Ohm's law is represented as voltage equals current times resistance, or V equals IR for short. So it's a very simple formula that we can manipulate to solve for any missing value. So down here at the bottom is a nice, easy way to remember Ohm's law and how to manipulate it to solve for what you need to find. For example, if I want to find voltage, cover up voltage, and I and R are next to each other at the bottom of the pyramid. This is supposed to represent V is equal to I times R. If you cover up what you want to find, what's left shows you how to find it. Let's say that I want to find current. Literally cover this up with your hand or your finger, and we have V over R. So we know that I equals V over R. Or if I want to find resistance, I know that resistance, if I cover that up, I get V over I. So I can solve for resistance by saying V over I. So we can use Ohm's law and some algebra to manipulate it and solve it for any missing variable that we want to. So here's our first example, where we're going to use Ohm's law to calculate the current flowing through R1 and the voltage drop across R1. So if you notice on the screen, we have a picture of a circuit. I have a voltage source. It's a DC source because of this symbol here. This is the symbol for a DC source, and it's set to supply 20 volts. Current is going to flow through these wires and through this resistor. As current flows through this resistor, we'll have a voltage drop across the resistor, which we're going to calculate. We're also going to calculate the amount of current flowing through the resistor. Here's our flow of current. Current is always going to leave the positive terminal of the voltage source, and the positive terminal is always the terminal with the longer edge. So if you think about a battery has a positive terminal and a negative terminal. Our voltage sources are similar. They have a positive terminal and a negative terminal, and current is always going to leave the positive terminal, flow around the circuit, and return to the negative terminal. So that's what we call our total our total current, or IT. This is the total current flowing through the circuit. So as we start to learn more about DC circuits, we're going to draw the direction of current flow, and we're going to label it. So in this case, we're going to draw an arrow like this showing how current flows and what direction it flows in, and we're going to label it with IT. IT means total current. As current flows through this resistor, we're going to get a voltage drop across the resistor. And the voltage drop has a polarity. Again, just like a battery that has a positive and a negative terminal, anytime current flows through a resistor, we have what's called a voltage drop, or a voltage that we can measure across that resistor. That voltage is going to have a polarity. The side of the resistor where current enters is a positive side. The side of the resistor where current exits is the negative side. So current travels this way. It enters the top and exits the bottom. So where current enters gets a positive sign, and where current exits gets a negative sign. And then I'm going to label that voltage drop as VR1. I don't know what it is yet. I'm going to calculate it, but for now I'm just going to call it VR1, which stands for the voltage drop across R1. Now I'm going to use Ohm's law to figure out the total current in the circuit. I know Ohm's law is V equals I times R. Well, I know how much voltage is applied, and I know how much resistance I have. So I can plug those two values in and solve for current. Now, I'm going to sort of rewrite my equation to represent the values we have in the circuit. Vs means voltage source, our 20 volt source. IT means total current in the circuit. RT means total resistance in the circuit. I'm adding a subscript of T here because we can find the voltage for just one resistor, like VR1, or we could have the voltage for the entire circuit. We could find the current just for one resistor, and we'd call that IR1, or we could have the current for the total circuit, IT. So that's where the subscripts come in. Now I'm going to fill in what I know. I know that Vs is 20 volts. I know that the resistance is 10 ohms. Notice that I not only wrote the number, I also wrote the unit. As you are writing your equations, do not just write down 20. It's 20 volts. Don't just write down 10. It's 10 ohms. It's very important that every number you write has a unit associated with it. Now that I've filled in what I know, I can solve for total current, which is going to be 20 volts divided by 10 ohms, which is going to give me 2 amps of current. The voltage for R1 is going to be the current that goes through R1 times R1. So notice I have different subscripts now. That's why we have to know how we're applying Ohm's law. We can apply Ohm's law to a total circuit or just to one piece of the circuit. So if I want to find the voltage just for R1, I need the current flowing through R1. In this case, the current flowing through R1 is the total current because there's only one path for current to flow. So the current flowing through R1 is my total current. And I have to multiply that by the value of R1 to get the voltage drop for R1. And I end up getting 20 volts. Sorry, that should be 20, not 20. So I end up getting 20 volts. And the reason why I get what I started with is because there's only one resistor. So all of this voltage is applied to just this one resistor. So I'm going to have all of that voltage drop applied to this one resistor. If we have multiple resistances in the circuit, we would see different voltage drops for each resistor. But this is just demonstrating how we use Ohm's law and how we apply it to a resistor versus our total circuit. Let's look at another example. In this one, I have a voltage source, I have a resistor R3, and I don't know how much resistance it has, and I have a current of 5 milliamps. We're going to use Ohm's law to calculate the value of R. First thing I know is the current flows this way, clockwise. I know that because the positive terminal of the voltage source is right here, and I can see the direction of the current flow. So I'm going to label that with my label of IT. I can see that IT flows through R3. I also know the value of IT. It's 5 milliamps. It's labeled right here. The current is 5 milliamps. And I know that as that current flows through the resistor, I'm going to have a voltage drop across R3. Remember to label the positive terminal where current goes in, the negative terminal where current exits. Now let's apply Ohm's law. I know that V equals IR. In this case, I know that means my source voltage, my 10 volts, is equal to my total current times my total resistance. And in this case, I only have one resistor in the circuit. So my total resistance is that one resistor. Plug in what I know, and I have 10 volts is equal to 5 milliamps times R. Remember your engineering notation here. Milli means times 10 to the negative 3. So I don't have 5 amps, I have 5 times 10 to the negative 3 amps. That means when I solve this equation for R, and I go to my calculator, and I type this in, I'm not doing 10 divided by 5. I'm doing 10 divided by 0.005, or 5 times 10 to the negative 3. Make sure you reflect the milliamps in your calculation, otherwise your answer will not be correct. So 5 milliamps is what we have on the bottom. 10 divided by 5 milliamps gives me 2,000 ohms, or 2 kiloohms of resistance. In our last example, we're going to use Ohm's law to find the missing value for each circuit. So we have V equals IR, that's Ohm's law. And in each case, one of those values is going to be missing, and we're going to solve for those values one at a time. So with the circuit on the left, I know the voltage, I know the current, I don't know the resistance. If this circuit looks odd to you, keep in mind that the connection down here is called ground. Ground is a common point of return for your current in your circuit. In a circuit, current has to have a closed path to follow. Ground is like your completion of the path and the point to which current returns to the beginning. It's like the closing of the loop. I can have one ground in a circuit, I can have multiple grounds in a circuit, and they all represent the same point, the same connection point. So I can have 2 grounds here. This just means that current flows this way, this way, this way, and back around to my source. So I'm missing resistance. I'm going to use Ohm's law to find the value of resistance in the circuit. R is going to be V over I. The voltage is 10 volts. The current is 2 amps. I end up with 5 ohms for my missing resistance in the first circuit. In the second circuit, I have a current, I have a resistance, but I don't have voltage. So I can use V equals IR to solve for my voltage. 2 amps times 47 ohms gives me 94 volts for voltage. And in the third circuit, I have a voltage, I have a resistance, but I don't have a current. So I'm going to use Ohm's law, but manipulate it to solve for current. I have 5 volts divided by 10 ohms, which gives me 0.5 amps, or 500 milliamps. And this is just a very basic introduction into Ohm's law. In our next video, we're going to learn how to apply Ohm's law to a series and parallel circuit. For our last example, we have a 5-band resistor that is connected across a 12-volt source. I want you to determine the current if the color code is orange, violet, yellow, gold, and brown. So this is tying 2 concepts together: decoding a resistor and applying that engineering notation, and then using Ohm's law to figure out if that resistor was connected to a 12-volt source, what's the current going through it? So let's start by decoding that resistor. Using our color code, we have orange, violet, yellow, gold, brown. Orange is a digit of 3, violet is a digit of 7, yellow is a digit of 4, and then our multiplier is gold. Multiplier is 0.1. And then our tolerance is brown, which is plus or minus 1%. So I have a 37.4 ohm resistor when I multiply my digits times the multiplier. And we're not going to worry about the tolerance here. We're just going to say, okay, that resistance is 37.4 ohms. Well, that resistance is connected to a 12-volt source, so we can use Ohm's law to figure out the current going through. V divided by R, so we have 12 volts divided by 37.4 ohms, and there's my current. So this is how we can combine multiple concepts into one problem to use Ohm's law. And that's the end of this video. Again, this is a very simple introduction. The next videos will become more complex as we look at DC circuits and how to use Ohm's law. If you have questions, here's how to contact me, and let me know if you need any help.